Welcome everybody to my talk. My name is Frank Steinicke. I'm a professor for human-computer interaction at the Department of Informatics at the University of Hamburg. And in my talk, I would like to talk about bending or blending artificial and virtual realities. So I would like to show how different aspects of virtual reality and artificial intelligence as well as robotics can be blended together in a so-called blended reality space. And a blended reality space is nothing special. Even our own reality can be interpreted as a blended space which is composed of the dichotomy of natural and artificial objects. And according to the German philosopher Bimbacher, the distinction between natural and artificial occurs at the impact level. So natural denotes everything which came without human being, whereas artificial denotes everything which was made by human impact. And although this distinction is central to our orientation in our real world, objects such as artificial flowers or genetically modified food already show the blurring between natural and artificial, illustrating a blended reality. And in my keynote, I would like to focus on three distinct aspects of mixed reality, intelligent virtual agents, and the Internet of Robotic Things, and show how we can blend them together to receive something that we call the ultimate blended reality experience. So let's start with mixed reality. As you know, mixed reality denotes the combination of real and artificial environments which are presented by some sort of immersive or semi-immersive technology. And mixed reality as we know it today dates back on the pioneering work of Ivan Sutherland, one of the creators of computer graphics. In 1965, Ivan Sutherland wrote a wonderful essay called The Ultimate Display. And in his essay, he speculated what an optimal or ultimate display would look like. And he concluded that this ultimate display would of course be a room within which the computer can control the existence of matter. So what would that mean? He gave some examples. So he said a chair displayed in such a room would be good enough to sit in. Handcuffs displayed in such a room would be confining, and a bullet displayed in such a room would be fatal. But he also wrote that with appropriate programming, such a display could literally be the wonderland into which Alice walked. So the ultimate display would be a computer-mediated reality which gets indistinguishable from the real world. And this notion of a virtual reality environment is often used in science fiction, cinematography, or literature to question whether we truly know if our perceptions are real or not. And movies like The Matrix, directed by the Wachowski siblings, is a prominent example of this perceptual ambiguity. Already 3 years later, in 1968, Ivan Sutherland and his team were able to build the first prototype of such an ultimate display. And what you see here is some original video footage from that time in which one of his team members uses the first augmented reality head-mounted display ever built. And on top of the user, you can see this linkage, which is basically responsible for tracking, and this was denoted the sword of Damocles. And the head-mounted display itself consists of a beam splitter technology, which allows to see the real world and superimpose it with virtual content digitally produced on this head-mounted display. Back at the time, of course, graphics was limited, and the only thing that users could see back at the time was this wireframe cube. But it hovered in space, and users could walk around by moving their head quite naturally, and very similar to our today's augmented reality displays. And this brings us to the definition of an augmented reality compared to a virtual reality setup. And this has been introduced by Paul Milgrom, this distinction. So Paul Milgrom defined the so-called mixed reality or reality-virtuality continuum. And the major idea is that we have two endpoints in this continuum. One denotes the reality as we know it today, and the other one denotes the completely purely computer-generated environment called the virtuality. So this denotes a multi-sensory experience in which all senses are basically stimulated by a computer. And in between, obviously, you can mix sort of virtual and real objects. And this brings us to the area of either augmented reality. That means we start with reality and now we start to augment virtual content. Or coming from the virtuality, so imagine a purely virtual environment in which we add some real-world objects, for example, a video of a real user. And this would be denoted as augmented virtuality. And everything in between denotes essentially the mixed reality continuum. However, this mixed reality continuum allows to combine real and virtual objects, but in the vision that we have for a blended space and blending reality and virtuality, we want more. And let's consider the three major examples of Ivan Sutherland's ultimate display. So he said a chair displayed in such a room would be good enough to sit in. So that means in one moment the chair could be diminished and I can't sit on it. But in the next moment the chair is added to the virtual environment and I can actually sit on the chair. And there is no need for me to switch glasses, for example, or change the display environment to be able to sit on such a chair. The entire experience would be seamless. And that's why we call this feature reality-virtuality seamlessness. In the same way, we consider the second example, which was handcuffs displayed in such a room would be confining. So that means that real objects can affect virtual objects and vice versa. And we will refer this ability of real and virtual objects to interact with each other as reality-virtuality interactivity. And finally, Ivan Sutherland wrote, a bullet displayed in such a room would be fatal. So that means that virtual objects can transform from virtual to real objects and vice versa. And we refer this to reality-virtuality transformability. And taken together, this denotes a blended reality space, so a reality-virtuality environment with one or more virtual objects or actors which support reality-virtuality, transformability, interactivity, and seamlessness. And still today, we don't have neither perfect virtual reality, nor do we have a perfect blended reality space. But for the remainder of my talk, I would like to argue that we don't need a perfect simulation of all our senses, since the perception action loop of the human being is limited itself, and we can use some of these limitations. So let us briefly go through the process how multisensory information is perceived and processed by humans. So we have multiple senses like the eyes or ears or our skin with which we process information either in a bottom-up way, which is a data-driven way, but to further process it in our cognitive processors. But at the same way, cognition also influences how we process this data, which is called hypothesis-driven perception. And when this information is now available in our cognitive system, we can, for example, perform certain actions, either in a top-down, so controlled way, but there is also some motor adaptation which influences basically how we perform the motions. And if we start now to send out corresponding signals to our muscles, so-called motor commands, we send an afference to our muscle system. And with this afference and muscles, then we manipulate the environment around us. For example, we press buttons or move our head, and then we observe feedback. We see new updates with our visual sense, but maybe also with our ears or with our skin. And this again then goes back in this loop of perception and action. And this works in the real environment, but it also works in a virtual environment, for example, with mixed reality. Whenever we perform such afferents or use such afferent signals to stimulate our muscles, in the same time we send a copy of the signal into a forward model. And this forward model is used for predicting the feedback that we perceive. And typically there is always a small discrepancy between the prediction of my actions and the actual observed sensory feedback. However, typically this discrepancy is rather small. So for example, in mixed reality environments, you might have tracking latency or inaccuracy or imprecision, which leads to some discrepancies. And as long as the discrepancies are small enough, we will even not notice and will just simply adapt our motions. However, you all might experience situations with larger discrepancies. For example, if you want to lift a box and the box feels much heavier than you thought, then you will see there is a big discrepancy between what you predicted and what you actually observed. So in this perception action loop, there are certain steps in which there are some limitations of the human perceptual action systems. For example, there's perceptual filtering, selective attention, and motor adaptation. And I would like to briefly talk about all these three aspects and give examples how we can use limitations in these aspects of the system. So let's start with motor adaptation. Motor adaptation means that while I perform my actions, I will adapt my motor actions, for example, based on the sensory discrepancy. So let's see how we can use this to make a blended reality environment and space more ultimate. So in the last sentence of Ivan Sutherland, he envisioned that the ultimate display would be the wonderland into which Alice walked. So the focus is here on natural exploration of a virtual environment by using your gaits, by using your locomotion and walking, rather than using a mouse, a keyboard, or some gamepad. To implement real walking in virtual reality is rather easy. You simply need a head-mounted display. You track the movements of the user in the real world and map those movements to the virtual environment. However, the problem is typically that the real environment is much smaller than the virtual environment. And that means that at one point, since you are not aware of your real world constraints, you might crash into obstacles in the real world, such as walls. And those things actually happen. So here's one example of a user playing a zombie game in VR. And as you will see in a second, she is afraid of the zombies, that the zombies try to catch her. And look what happens.
You almost don't get the knife. Oh, shit.
So as you can see, with a high sense of presence, so the illusion that you are really in this virtual world, you forget about the real world around you. So my group has spent now 1.5 decades or so to think about how can we solve this problem of allowing people to explore an omnidirectional virtual environment which is much larger than the physical space that they can use, for example, a lab or a living room. And here's an example of some technique called redirected walking, which was originally introduced by Razak and colleagues at the UNC in Chapel Hill, and we have extended this approach. So imagine that you wear a head-mounted display, for example, in your living lab, and now you see a virtual chair. Just remember, Ivan Sutherland said a chair displayed in such a room would be good enough to sit in. Of course, you can't sit on a virtual chair. However, if we can predict that the user wants to walk towards this chair, while the user is walking, we can slightly rotate the environment around the user so that the user, in order to walk towards the chair, need to walk on a real path which is curved, while he or she believed to have walked on a straight path in the virtual environment. And the interesting thing is now that due to this rotation, the virtual chair is now co-located with the physical chair. So the physical chair could provide passive haptics and the user could actually sit on this virtual chair. So a chair would be good enough to sit in. First challenge solved. However, we performed a series of experiments in order to identify how much we can actually trick users. And as you can see in the graphics here at the bottom, even with today's technology, we still need about 10-meter radius so that you do not observe that you actually walk on a circle in the real world while you believe to walk straight in the virtual environment. But we can further shrink these circles. One example is the usage of perceptual filtering. So in visual science or vision science, we know that when we explore the environment with our eyes, we have different situations. So there are fixations. That means you focus on certain points in your environment. But we also have blinks, so when we close the eyes. And we also have saccades, so these are micro movements of the eyes to get to the next fixation point. And while most of the perception research was focused on fixation in previous years, we also started to explore eye blinks and saccades for redirected walking. Since during those blinks and saccades, which happens approximately almost once per second, we are literally blind for about 80 to 100 milliseconds. So that means visual input is suppressed approximately 1/10 of the time. And we would like to make use of this time frames. So here's one experiment which has been conducted by my former postdoc Eike Langbeen, who is now a professor at the HAW in Hamburg, and he will also talk about this probably a little bit more in detail later. But what you can see here is that we used the eye blinks, which we detected with an eye tracker in the head-mounted display, to induce changes in the virtual environment, as illustrated here. And if we combine this manipulation during an eye blink with redirected walking, we can further improve redirected walking by approximately an additional 4 to 5 degree manipulation, as illustrated in this video. So you see a user who is redirected while walking on this corridor, and in the moment of the eye blink, there is an additional rotation which further manipulates the user by walking, for example, on a circular arc. But we can also use the imperfections of the perception action loop in the cognitive processor. And here's one aspect called selective attention. That means I need to pay attention to certain objects to bring them in my short-term memory. Otherwise, they will just get lost in my sensory registers. And here's one example how we can use this. So here's an example of one of my PhD students. She needs to grab in the virtual world a virtual sphere, this blue sphere at the bottom, and we provide passive haptic feedback with a real sphere. And as you can see, she grabs now the sphere, she walks out of this room, she walks along the corridor, and she enters the room next to the other room, and now she has to put the sphere on the table there. And the interesting thing is, while those have been two different rooms in the virtual world, in the real world, actually those rooms would have overlapped, and she was using the same physical representation of the sphere and the same table here. And this works because she did not really pay attention of how the rooms were arranged, because in the moment she left the one room, she kind of forgot in her short-term memory about the first room and entered the second room and did not notice that those rooms actually would overlap in the real world. So that's it for now for mixed reality. Let's go to the next point, which brings in artificial intelligence to mixed reality environments. And this can be done by intelligent virtual agents. Artificial intelligence is defined as human intelligence simulated by a machine. And the question is, how can we define if something is an artificial intelligence? So does it appropriately simulate human intelligence? And to answer this question, Alan Turing provided a behavioral stance. So in particular, he asks, well, can machine think? Or in other words, can they do as we do? And therefore, he proposed the so-called Turing test, or the imitation game. In this test, you have a real user C who participates in an experiment in a dialogue-based, text-based communication with either A, a computer system, or B, a human. And in this case, if A, the computer system, is able to trick or fool the user in making him or her believe that A is actually a real human, then A would have passed the Turing test. And the interesting thing is, in order to pass the Turing test, you don't have to program a super intelligent machine, but rather opposite. You also have to implement unintelligent behavior of humans, since humans are not always intelligent. And for example, if you ask a human, what is the square root of 4,467,000, no human would probably be able to answer this immediately. And also a machine should mimic this imperfection of humans. And here's one example of my postdoc Susanne Schmidt, who implemented some imperfect intelligent virtual agents which simulate also non-intelligent behavior. And look at this example, please.
Hi Louise, have you seen Frank today?
Yeah, I saw him in the lab around noon.
So what you have seen in this example is that first of all, the agent does not look perfect. Yeah? She's beautiful in my eyes, but still she has some birthmarks and blemished skin. In addition, when she was asked something, she started to look up and right, which simulates more or less what we humans do if we need to remember something visually. And also she was thinking for it. It suggested that she was thinking for the answer. And there was also stutter and delay sounds such as And then also her answer was not really precise. She said something like around noon. Of course, she would know exactly the minute when I entered the physical lab. But all this simulates the imperfection of human communication. And we believe that this has also great potential, for example, to improve natural communication, for example, with agents, but also to improve the trust or social presence when interacting with intelligent virtual agents. It might also be an interesting approach to, for example, better display and represent, for example, transparency and provide explainable intelligent virtual agents. Okay, let's see how we can bring together the Internet of Robotic Things in this approach. The Internet of Robotic Things is a rising topic which brings together autonomous robotic systems with the Internet of Things. And here's one example of one of my former postdocs who implemented a Microsoft HoloLens application which allows to use natural communication in order to control a shadow robot, as illustrated here. So you see that in this case we have a real robot, which is the shadow hand here, which is in the same space as the user. And you see a digital twin, so let's say a virtual assistant of this robot arm, which can be used for pre-visualization. In a similar way, here is my now postdoc Jingxing Chang, who just defended his PhD during this week, and he works in telepresence systems in which he collaborates with remote users which are represented by a telepresence robot. And in this case, he embodied the telepresence robot by a human being or a human avatar as illustrated here. And this illustration, for example, might help to better grab and understand the intentions of, for example, a robot system and, for example, prevent collisions. So how can we bring this all together? Mixed reality, intelligent virtual agents, and the Internet of robotic things. And here's one example in which we try to combine and blend all these different aspects together. And this is work which has been conducted by my postdoc Susanne Schmidt. And you will see a virtual agent who is displayed in a cave, but who is also able to interact with real-world objects, as illustrated in the following video.
The first interaction is based on a robotic golf ball. Through a weight shift inside the outer shell, the ball can move with 3 degrees of freedom with a maximum speed of 1 meter per second. We designed a user study within a cave that simulated a mini-golf match between the participant and a blended agent. The animations of the blended agent were synchronized with the movements of the robotic ball, resulting in the illusion of the agent hitting the ball. The agent played the ball along a predefined path into the hole. Afterwards, the agent headed back to a table at the entrance of the mini-golf course to record her score using a prepared scorecard. In this context, we demonstrated our second virtual physical interaction, persistent writing on a sheet of paper using a thermal table. The table is a custom-built device to activate thermochromic ink on a sheet of paper via temperature variation. Initially, the blended agent writes a projected score onto the sheet of paper. In the course of the mini-golf match, the temperature is switched from high to low, and the previously transparent ink turns black. Therefore, when the user takes the scorecard outside of the mixed reality environment, the score is still visible as it is physically written. Participants of the study described the experience as fascinating, more realistic, and memorable. Further information can be found in the paper.
So this was one example which shows how we can build a blended reality space which allows reality, virtuality, transformability, interactivity, as well as a seamless display. So let's see how this might evolve in the future. The good thing about computer science is that we can easily extrapolate how technology will evolve. Since 100 years, we know that computing technology and computing power evolves exponentially. So that means every approximately 1.5 years, we will have machines which are double as good as the machines that we have nowadays. And this was true for the 60s, it was true during the 90s when the first VI hype arose, and it's also true today. And with this knowledge that we know that technology is getting double as good every 1.5 years, we can extrapolate how good technology will be, for example, in 15 years from now. So since we know in 1.5 years technology will be double as good as the technology that we have today, we know that it's going to be 4 times better in 3 years. And we know it's going to be 8 times better in 4.5 years, and so on. And if you continue doing this math, you will quickly come to the result that within 15 years our technology will be 1,000 times better than the technology that we have today. And just think about what this means. If your technology, so the bandwidth, storage, and processing power is 1,000 times better, that means that we move, for example, from mega to giga, from giga to tera, and so on. And there are certain problems that we will just solve in case technology will be 1,000 times better. One example is the so-called graphics Turing test. So the graphics Turing test is a variant of the traditional Turing test I just showed you, but the idea is here that you need to render virtual objects which gets indistinguishable from real-world objects. So think about a computer game in which you can't tell if the displayed environment was video captured or if it's computer generated. And we already have such environments, for example, in Hollywood blockbusters. The challenge is here to do this in real time, so like in a computer game. And it's pretty clear that with the current GPU performance that we have, which is in the range of maybe 10 teraflops, that we will be able to solve this issue, because it has been calculated that we need about 1 petaflop of sustained rendering performance. And this will be probably reached within the next 5 years or so. And that means that we will be able to render computer-generated environments, virtual worlds, which we can't distinguish from the real world anymore. And this, of course, raises a lot of ethical, legal, and societal questions. And here's just one example of what being 1,000 times better means in computer graphics. So when I finished my high school in 1996, I played some computer games, and one of the best games back at this time was Tomb Raider. And Lara Croft was looking like this in 1996, and that was kind of the best rendering you could get at that time. About 1.5 decades later, so being 1,000 times better, Lara Croft was already looking like this. And 3 years later, she was looking like this. And this is exponential advancements. And if you just continue thinking about how this technology will evolve in the future, it gets really clear that within the next 5 to 10 years, we will have environments from which we cannot tell anymore if they have been computer generated or not. And as I said, there will be a lot of challenging questions regarding, for example, fake news, trust, etc. And at the same time, we will also observe that head-mounted displays will shrink. And they will eventually get the side of a contact lens. So contact lenses might be the future smart glass with which we explore, for example, the metaverse. And all big players have already filled in their patents for such contact lenses. And that means if the head-mounted display technology will further shrink and get more comfortable, surely within the next decade or so, we will observe that the era of smartphones will more or less end and come to an end. And at the same time, we will see more and more other devices. And I believe smart glasses might be the next era, which will replace smartphones. And actually, we already observed this for the first time in the last 1 or 2 centuries. We see here that the global smartphone shipment market has decreased for the first time since 10 or 15 years or so. And only in the Asian countries, in China, we see a little bit of increase, whereas in particular with other suppliers, like for example Apple, the number of sellings really have gone down within the last 2 or 3 years. And I'm really looking forward to work together with you on developing such new blended spaces which allow to blend reality and virtuality, which allow to blend human intelligence and artificial intelligence. If we consider this continuum, we see that only virtuality, so a purely computer-generated environment, is just a point. And at the same time, we see that only having reality, it's also only a point. But the combination provides new potential. And the same happens with intelligence. If we only consider human intelligence on the one side, or only purely computer-generated artificial intelligence, again, we see that those are only 2 points, and there is not much possibilities what we can do with this. The real magic is in the blending between reality and virtuality, between human intelligence and artificial intelligence. Thank you very much for your attention.